Good morning, live from Compound, coming to you for Module 11. So, Module 11 is all about residential electrical services. Just quick background information on this. The use of electricity in houses began shortly after the opening of the California Electrical Light Company in 1879 and Edison's Pearl Street Station in New York City in 1882. The two companies were the first to enter business in producing and selling electrical service to the public. In 1886, the Westinghouse Electric Company secured patents to result in the development of the introduction of alternating current, and this paved the way for rapid acceleration in the use of electricity. Primary use in early home was to provide interior lighting. So I have been in a few homes around this area even that have been that have old fixtures that were converted back when electricity became popular here and was available, that the old gas lights were then converted over to electric lights, and they're still in operation, they're still used, and it's really kind of a neat way of looking at it. That was the reason why people had electricity in their home, just to take the place of the gas for lighting, because it was safer, it was cooler, and it didn't put uh, all of the carbon monoxide into the air as it was burnt. It was really a great leap forward, as much as going from a incandescent lamp to an LED lamp is now a great leap forward uh, for everyone when they were able to move move away from the gas lights, or even the coal oil, or kerosene, uh, or lamp fuel, and be able to use electricity to light their homes. Uh, our what we have what we use electricity for now is so much greatly expanded that people then wouldn't have ever guessed that we would be where we're at today. Um, you think about all the demands for electricity now: heating and air conditioning, electrical appliances, interior and exterior lighting, communication systems, alarm systems. So there's so much draw on the electrical services now that wasn't there 150 years ago when it was first being installed in the homes. That we've come a long way. So uh, there's many things to think about when you're laying out a house, and there's different loads that are going to be necessary, but you have to. We're going to break them down and look at each one individually. So as you think of um, what needs electricity in a home when you go to wire it, you'll break it down into different categories, different things. One of them is general lighting load. Uh, General lighting loads are calculated on the basis of the NEC table 220.12. This is critical information here. 220.12 for residential occupancies, 3 volt amp or watt per square foot of living space is the figure used. So you need to know how you figure for that, and it's 3 watts per square foot of living space. And that gives you what your code for lighting load will be. So when you figure that, when you take your plans, you have to figure how much draw is going to be for lighting. And you just take your living space. So that includes kitchens, bedrooms, living rooms, utility rooms, but not bathrooms. Those don't count within living space. So when you then figure your demand, that is what you're going to get for whatever size house you're planning out. It doesn't include the garage either. If there is a garage, that doesn't count as living space. Another area you're going to need to figure, your small appliance loads. Think about where are you going to have small appliance loads. Small appliances are an NEC. Here's key information, good notes to have. NEC section 210.11C1 requires at least 2 120 volt, 20 amp small appliance branch circuits to be installed for the small appliance loads in each kitchen area of a dwelling. So if you have just one kitchen, then that is what is required at that kitchen. If you have a duplex in this house and they're on the same meter, well, you're going to have to figure for 2 kitchens. That means you're automatically going to have 4 120 volt, 20 amp small appliance load branch circuits in each one of those. If it's a triplex, if it's a quadplex, you're going to do the math. Or if it's a home that has an upstairs kitchen and a downstairs kitchen, then you're going to have to figure that within and stay within code. So you're going to need to be able to plug in a coffee pot, a toaster, a blender, a mixer, a whatever small appliances you can think of, crock pot. Those things are going to have to be able to be plugged in that kitchen so that it can be used for cooking or whatever you need there. And that's going to be within code. That's going to be one of those things that you're going to have, and that's a good note to have written down. You have your laundry circuit. Laundry circuit says that, and again, in section 210.11C, and this time 2, requires an additional 20 amp branch circuit to be provided for the exclusive use of a laundry area. So you need to have that. Lighting demand factors. Residential electrical outlets are never used. All electrical all residential electrical outlets are never used at one time. There may be rare instances where all the lighting may be on for a short time every night, but even so, all the small appliances and receptacles throughout the house will never be used simultaneously. Knowing this, the NEC section 220.42 allows for diversity or demand factor to be used when computing the general lighting load for services. Our calculation continues down below here. I believe you have a slide that shows that. That's just good to be able to know. Demand factors are something that you run across to, and within residential, like it says there, you're not going to be doing everything all at once. So you're going to have a demand factor that continues to drop as you add more to it, because not everything's going to be working at the same time. And you can get into that demand factor as you see it there. Simply put, the first 3000 volt amp or 3 kVA is rated at 100%. After that, the remaining if you look at box or figure 3, I think it is here, maybe the remaining 5,550 volt amps may be rated at 35%, the allowable demand factor. And then net general lighting and small appliance load rounded off, and you get your demand factor. So there are certain things that you're going to have in there that are fixed appliances. This is good to know, and you need to know what the NEC says about fixed appliances. The NEC section 220.53 permits the loads for 4 fixed appliances in a single family dwelling only to be computed at 75%. So your fixed loads, your hot water tank or your water heater, that is going to be your 4.5 kVA. Your dishwasher is 1.5 kVA. A gas furnace blower, I skipped one. A half horse disposal is 1.176 kVA. Gas furnace blower is 464 volt amp. And so you add those together, you get 8,040 volt amp or 8.04 kVA, but those in your demand factor are going to be computed at 75%, because you're not going to be running your water heater at full, having had dumped your water heater and now it's working at full capacity to heat the water back up. It's a cold water heater, not a hot water heater. Remember that. There's no need in heating hot water. It's already hot. It's a hot water tank, a water heater, not a hot water heater. Your dishwasher and your hot water and your disposal and your furnace blower, the likelihood of them all being on at the exact same time at full load, everything kicking on at the same time, is so highly unlikely that the NEC says you can figure them at 75%. So you just think about, as you go through, you've wired a house, you know what the different loads are, and this is part of figuring in for those loads. Now as you go in, you're looking at your small appliance loads, your laundry circuit, your dryer load, your range load, demand factors for electric ranges. Those are laid out in the NEC section 220. One thing you need to know about your electric range, when you're sizing residential neutral conductors, you need to know what is able to be done. Most of the time, you're not even going to figure anything differently. You're just going to do what's already in a jacket, what's already made up in Romex. But you should have this in your knowledge. An electric range is rated at 8 kVA. So when you figure that at 70%, that is 5.6 kVA. And a clothes dryer is rated at 5.5 kVA, 70%. You're looking at 3,850 volt amp. So as you're sizing your neutrals, you can, that load factor can come into play, but you're going to know that you're going to have that available. You're going to run that 6.3 with ground to the range. You're going to run that 10.3 with ground to the dryer. But again, you need to know that your electric range is uses that 70% factor, and the clothes dryer uses that 70% factor. The neutral conductor in 3-wire single-phase services carries only the unbalanced load between two ungrounded hot wires or legs. Since there are several 240 loads in the above calculations, these 240 loads will be balanced and therefore reduce the load on the service neutral conductor. Consequently, in most cases, the service neutral does not have to be as large as the ungrounded hot conductors. That's why you can get by with a downsized neutral in a service. But you also have to think what's available when you start running your service entrance cable. It's already, generally the math is done for you. If you need a certain size hot, then you're going to have the right size neutral within that jacket. Moving on, sizing load center, you figure that as far as what you're going to need for your kitchen. You lay out the house and you do all the figures according to NEC, and you see, what am I going to need here? What's my demand going to be? What's my power factor going to be? And then you plug it all in and you say, oh, okay, I need a 200 amp or I need a 400 amp service at this place because of yada yada. as you go through, there are different things that you have to work into having into the uh, into your home. And one of the things as you're going through, you're going to have to figure for uh, ground fault circuits, not either using ground fault receptacles or ground fault uh, breakers, but you're going to have one or the other on certain circuits. What you need to have in mind, what's a good note to file away for you, Class A GFCI trip when the current to ground has a value in the range of 4 milliamp to 6 milliamp. So a Class A GFCI will trip when the current to ground has a value in the range of 4 milliamp to 6 milliamp. You need to know it's 4 milliamp is that low end there. That's the range where it needs to be. Remember, this is a safety device, so if it's detecting a bleed off, it's going to trip to save a life. Further requirements for GFCI protection are receptacles within garages. Receptacles within garages. Good note to have, good idea in your head. You have to have GFCI protection in a garage. This is something that you might come across and somebody might have issue with, but for code, you have to have GFCI in your garage, even if it is for a freezer or a refrigerator or whatever. It has to be GFCI protected. Going on with GFCIs, the GFCI sensor continuously monitors the current balance in the underground or current balance in the ungrounded or energized hot load conductor and the neutral load conductor. So it's always monitoring, always looking at the balance. So good to have up here. The GFCI sensor continuously monitors the current balance in the ungrounded or energized hot load conductor and a neutral load conductor. So if the current in the neutral load wire becomes less than the current in the hot load wire, then a ground fault exists. It means it's shunting off, it's going another path to ground, and there's an unbalance and it will kick. It's always good to be able to explain that and be able to say, hey, this is why this is a life-saving device. So you have single pole and two pole GFIs. Those and there are GFI breakers or GFI receptacles available. There are also the arc fault interrupters. Talks a little bit about ACUs. The arc fault circuit interrupters are one of the things that another way of monitoring to make sure that if there is an arc, if there is something that causes a spark, it will trip it. It will cause it to stop allowing the flow of electricity because it says there's a danger there. Those are things that they've worked on. I remember when they were first implemented back in when was it? The early 2000s, probably 03, 04. They were kind of touchy. If you had something that didn't have an on and off switch on it, and you plugged it in, it could trip that arc fault, and you wouldn't have power there. It would, because it was showing that little bit as you plug it in, and the electricity reaches out, it throws an arc, and it says, "Oh, hey, there's a problem here." Grounding electrodes. To NEC Article 250, Part 3, provides the requirements for connecting an electric service to the grounding electrode system for a building or structure. NEC Section 250.50 requires in general that all electrodes described in NEC Section 250.52a be used if present, and they must be bonded together to form the grounding electrode system. The electrodes listed in NEC Section 250.52a are as follows. So grounding electrodes, your ground, what you're going to connect to for ground, and the electrodes are listed as follows. One of them are metal underground water pipe in direct contact with earth for 10 feet. That's one you need to know. Metal underground water pipe in direct contact with earth for 10 feet. It has to be a minimum of 10 feet. It has to be metal, and those are the requirements. Those are what has to be there for that grounding electrode. You need to know that one. You need to have that in mind. That's one thing that the book wants you to know. The metal frame of a building or structure complies with NEC Section 250.52a2. An electrode encased by at least 2 inches of concrete may be used if it is located within a near bottom of a concrete foundation or footing that is in direct contact with earth. So if it's in concrete, it has to be in contact with earth through it. Grounding ring encircling the building. A rod or pipe electrodes shall not be less than 8 foot in length and consist of either pipe or rods of iron or steel, and plate electrodes. So stainless steel rods, non-ferrous rods, or their equivalent shall be listed not less than ½ inch in diameter. So all this is what is code. Plate electrodes and other metal underground systems are all laid out there in NEC. So grounding is key, especially as we get more and more into having more electronics and more things that are sensitive to spikes, and especially in our area, lightning strikes within an area. Even if the lightning strike is ½ mile away, that's really close and can cause things to go kind of crazy within your system, within your house, and show a small spike here or there that doesn't get balanced out quickly, and it can cause problem. So the better the grounding, the less likely that imbalance is going to fall into your house, come into your electronics, but you'll have a better option. It'll have a better option to ground. Uh, you need to know GECs. You need to know grounding electrode conductors. NEC section 250.62. This requires, have this in mind, this requires it be made of copper, aluminum, or copper clad aluminum. So your grounding conductor needs to be copper, aluminum, or copper clad aluminum, so that it may conduct electricity well. And that's what you connect to your grounding rod, or your ground, where you're grounding your system at. So as we go through, you get into some of the service companies issues that they have to deal with, and you're going to have to work with them. Vertical clearances for service drops. You have to make sure that the distance of your service drop conductors clear the ground by the right height. You also need to know that it can't go over too much roof. And so there's different things, but you'll work with an engineer to set it up where it needs to be to make sure that you're going to be within code. Everybody wants to work within code. Everybody wants to be in the right spot. So you're going to work together to do that. The good note to have, and talking about the vertical drop, the conductors must be at least 15 feet above the ground. However, the distance may be reduced to 12 feet when the voltage is limited to 300 volt to ground. So when you're looking at what the electrical companies, what the linemen are going to call low voltage, when you get below 300 volts, you can drop that to 12 feet, but it needs to be about 15 feet. So that's why you get into having certain height of riser pipes when you're putting in a service. But you need to know that 15 feet above the ground, however, the distance may be reduced to 12 feet when the voltage is limited to 300 volt to ground. Well, it's going to be lower than that. So 12 feet is what you're going to be looking at. Now, panel board location. The main service disconnect, or panel board, is normally located in a portion of an unfinished basement or utility room on an outside wall, so that the service cable coming from the electric meter can terminate immediately into the switch or panel board when the cable enters the building. Okay, this is in ideal situations. The main service disconnect or panel board is normally located in a portion of an unfinished basement or utility room on an outside wall. But there are many different reasons why you do or don't do a back-to-back service. So, NEC section 230.70 requires that the service disconnecting means be installed in a rapidly accessible location, either outside or inside the building. So if you're not back-to-back, and back-to-back by, I know AEP standard says back-to-back is within 3 feet, no more than 3 feet of SEU, then you can use, you don't have to have a disconnect on the outside. That is considered back-to-back. But any more than that cable, then you need to have your outside disconnect as well as going into a panel. So most generally, everybody is now putting the meter-based disconnect combination unit on the outside of a home and running, whether it is back-to-back or not, running that into your home, and then you have your main inside means of disconnection. So you see that NEC section 230.70 requires that the service disconnection means be installed in a readily accessible location, either outside or inside the building. So you need to, that's another reason why having a disconnect on the outside is a safety feature. Going on, as we start looking at cables, wiring methods, cable systems, non-metallic sheath cable, non-metallic sheath cable, or NM, commonly referred to as Romex. That's one of those things you need to know. That's what you got to have in your head. Type NM cable is often referred to as Romex. Romex is a brand name. It's like calling all your acetaminophen Tylenol, or all of your ibuprofen Advil. It's the same thing. Or those self-adhesing bandages, calling those Band-Aids. It's a trade name. So to call Romex instead of type NM cable, it's just a matter of language, a matter of what you call it. I worked with a guy that called the nail plates or striker plates, he called them Dottie plates. He grew up in Southern California. Out there, the trade name for those was Dottie plates, because the Dottie company made them, and that was what they were used to using. So you just you have to know that Romex is a type of NM cable. Where cable runs through wood joists, here's another good note for you, something good for you to keep in mind as you're wiring up or doing anything. Where cable is run through wood joists, where the edges of the bored hole is less than 1 1/4 inch from the nearest edge of the stud, or where studs are notched, you need to install a steel plate, a striker plate, a nail plate, whatever you want to call them, to be within code. So 1 1/4 inches in, or it requires a nail plate. That's a good thing to keep in mind. Now, as we get into different types of cables, we have MC cable. I think everybody knows what the MC cable is. We had some in the shop. It's the ridged aluminum jacket over the, it can be solid or stranded wire inside. Type MC cable must be secured using staples or straps at intervals not exceeding 6 feet. You need to have that in mind. MC cable has to be secured by approved staples or straps at intervals not exceeding 6 feet. And you also need to know allowable radius for locked armor or corrugated sheath, depending on type. You need to know that 7 times D. D is your diameter, and your radius has to be 7 times. So you can't bend it too tightly around a corner. That's why they put that in there. That's why they have to say don't do this, because if you bend it tighter than that radius, it will break the jacket. No longer is that wire protected. So type SE cable, when used as service entrance conductor, must be secured every 30 inches. That's a note you need to have. That's something you need to keep in mind. NEC Article 250 Part 4 covers equipment grounding and equipment grounding conductors. To become energized, be grounded under the following terms. That's metal parts or fixed equipment likely to become energized to be grounded under the following conditions: where equipment operates with any terminal at over 150 volts to ground. So when you think about your equipment that you're going to have in a home, anything that's 240 has to have the ground requires that exposed non-current carrying metal products of a fixed equipment likely to become energized to be grounded under the following. So the chassis of the dryer, if you have the oven inserts in the wall, if you have an electric range, if you have a range top, those type things, if it's likely that that chassis could be energized, it has to be grounded. That's one of those things you have to have in mind. Listed FMC is permitted to be used as equipment grounding conductor only when the following conditions are met. And the one that you need to keep in mind here is the circuit conductors contained in the circuit are protected by overcurrent devices rated at 20 amps or less. So the flexible metal conduit or liquid type metal conduit are permitted to be used as the ground only when it's going to be less than 20 amp, the device is. So you can't use the jacket on your seal tight to be the ground to your air conditioner if the air conditioner is 20 amp or more. That's a good thing. You got to carry your ground with it. You got to keep that in mind. just a little bit more, and we'll stop for the day. Uh, this is a fairly long chapter or fairly long uh, module, and I want to make sure that I get it all in. But branch circuits and feeders. Branch circuits, the conductors that extend from the panel board to the various outlets are called branch circuits. A feeder consists of all conductors between the service equipment and the final overcurrent device. So you have to keep in mind, and you have to have this in your vocabulary, the difference between a branch circuit. Your branch circuit is what feeds the receptacle or the device itself, and the feeder consists of all conductors between the service equipment and the final overcurrent device. So you're talking a feeder is anything between the service and the breaker or the fuse, depending on your application. And that will be your what a feeder is. So I believe you've got figure 27 in your slides, and it shows what a feeder is, and then it shows a branch circuit. So you have that clearly in mind. And then as we go on, talks about multi-wire branch circuits. Those are simply as you go and continue on with different receptacles and different things like that, you'll have multi-wire branch circuits. And I think I'm going to cut it off right there. We've gotten a lot of material. It's telling me I'm at 47 minutes right now, so we will stop here and we'll pick it up and finish it up later this week, and then we'll send out another piece for everybody to work on. If you know that you're working and getting stuff done, but you know somebody else that hasn't been, get on them. We need to have this stuff done. Need to be able to turn something in. So get everybody on board. If you're still having trouble, let me know. And otherwise, I will see you later.